BackboneFast is another Cisco proprietary extension to the spanning tree protocol. The purpose of the BackboneFast is to allow switches to find an alternative path to the root should they lose their root port. In order for BackboneFast to work, it needs to be enabled globally on the switch, which means it cannot be enabled only on some interfaces or some VLANs. It's a global operation on the switch. Furthermore, in order for it to be effective and fully operational in our network, the BackboneFast must be enabled on all the switches in the network. The reason for that is because of what happens once the BackboneFast is triggered. I'll talk about it in a few seconds. What triggers the BackboneFast? Well, what triggers the BackboneFast is the loss of BPDUs on the root port. Or not only that, but what happens if we receive a superior BPDU on one of the ports that is blocking? If we receive a superior BPDU on the blocking port, that means that we should no longer be blocking on this port if this is indeed a better path to reach the root. But we cannot do that immediately in traditional spanning tree because we have to wait for the max edge to expire. And that adds 20 seconds to the complete convergence, to the full convergence in our network. BackboneFast aims to bypass the max edge timer. But in order to do that, it really needs to determine whether the new path through the blocking port is indeed the best path to reach the root instead of the current root port that we have. In order to determine that, the switch needs to interactively figure that out. And it is going to do that using another Cisco proprietary protocol called the root link query. The root link query is a protocol that looks very similar to spanning tree if we would to look at it at the frame level. The format is just about the same. However, the address to which it is sent is not that of the spanning tree. In a case that we have some switches that don't understand the root link queries, we wouldn't want to confuse them. So if they receive these frames, they're simply going to ignore them, and the switch that generated the root link queries is going to have to go through the standard spanning tree convergence instead of the slightly faster one using the BackboneFast. There are two components of the root link query. There is the request message and the response message, and as you are used to by now, I'm going to show them in action. Before I jump into the terminal and start showing you BPDU frames and bits and bytes in their headers, let's take a look at the example in which the BackboneFast can be of use and speed up the convergence in our network. For that, I'm going to use the network of 3 switches. They are going to be my Cat1, Cat2, and Cat3. Cat1 will be the root in this network, and my switches are going to be interconnected in a triangle that looks like this. This is going to be fast in a 24, and this is going to be fast in a 24. This will be fast in a 020, and this will be fast in a 020, and this one here will be 22. Given the network like this, with all equal cost links and with Cat1 being the root, the converged spanning tree topology will be that these 2 ports are designated ports, that this becomes the root port, this becomes the root port, this becomes the designated port, and this one here will be the blocking port, which means we are not going to be sending any BPDU frames on this port here. Now, what would happen to the traffic on, let's say, hosts behind Cat2 here, should the link to root fail? So if this link here fails, what's going to happen is that Cat2 will immediately transition to become a root. Why would it become a root? Well, because it's no longer receiving BPDU frames from Cat1, and because this here is a blocking port and by definition it doesn't send any BPDU frames, Cat2 now thinks it is the root bridge, which means that this here remains the designated port. But now Cat2 starts sending the frames that from Cat3's perspective here are inferior. Why are these frames inferior? Well, these frames are inferior because it is still receiving frames from the good root, from the route that was already elected in our network. And if cat1 was elected root in the network consisting of cat1, cat2, and cat3, with all links being up, it is still going to become a root. It is still going to remain a root from cat3's perspective, even though this link between cat1 and cat2 is down. So when these frames start arriving to cat3, cat3 is not going to accept them immediately. It's not going to do anything about them for the duration of the max age timer. The max age by default is 20 seconds. Once these 20 seconds expire, well, it's not exactly 20 seconds. I should make it clear that there is going to be the time between the previous frame being received and the 20 seconds, but it's going to be around 20 seconds, but it's not 20 seconds exactly. This timer is max age minus the lifetime of the frame. But those are really semantics. So let's say that after 20 seconds, Fast Ethernet 20 here is going to start transitioning from the blocking phase into a listening phase. Here we are going to listen for the incoming BPDUs. At this point here, we are going to start forwarding the frames from the good route out, because when we transition to the listening phase, we are going to start forwarding the BPDUs. When these BPDUs arrive to cat2, it is going to stop sending these frames here, and it's going to realize that there is a better route in our network. But this port here, Fast Ethernet 20 on cat3, is still in a listening phase, and it's going to remain there for 15 seconds. After that, we are going to move into the learning phase, where we are going to remain for 15 seconds, and only after that we are going to move into the forwarding state, where this port here becomes the designated port and this port here becomes the root. But all during this time, until this here happens, until this port transitions into the forwarding state, these hosts behind cat1, hosts A, B, and C, are effectively cut off from the network. For how long? Well, for 20 seconds plus 30 seconds here. That means that for around 50 seconds, these hosts cannot communicate with the rest of the network. This is how the traditional spanning tree would converge. Let's see that in action. So I have the configuration here on my cat1, cat2, and cat3 that matches the diagram that I was just explaining. So if I do show spanning tree on cat1 here, I will see that I have two ports, and they are both designated ports, and they are both forwarding. In cat2, if I do show spanning tree, I will see that I have two ports. One is designated, the port facing catalyst 3, and Fast Ethernet 24, the one facing cat1, is the root port and is forwarding. On cat3, as expected, I will have two ports, of which one will be blocking, the one facing cat2. Let's now go ahead and shut the link down between cat1 and cat2. Before I do that, what I'm going to do is I'm going to go to cat3 and I'm going to say debug spanning tree events. What I want to see with this debug is what happens when I shut that port down. Also, on cat2, I'm going to prepare the show spanning tree output. I will have to be rather quick with this. I have to do this show command within 20 seconds after shutting down the port. So I'm going to go to cat1, I'm going to shut the port down, and I'm going to wait on cat2 for the interface to go down, and then I'm going to do show spanning tree. I will go back to that output, but what I want to show you here is that now on cat3, I'm receiving information about the new route. If I go back to cat2, I see that this bridge is the root, which means that this port, Fast Ethernet 20, is now designated port. However, the port on cat3 has only now, just before I switched to this terminal, changed topology, changed the state into a listening phase. And we can see here that when that happened, we sent a topology change. Now, we can see here that Fast Ethernet 20 is now listening. It transitioned into the learning phase, and only now it has transitioned into forwarding state. That means that since I've done shutdown until this moment here, before this highlighted line here happened, there was no communication between hosts that may have been behind Cat2 and the rest of the network, because the link between Cat2 and Cat3 was being blocked on Cat3 side. It was being blocked until the max age timer expired. When the max age expired, then while the port was transitioning through the listening and learning phases of the spanning tree, the traffic was still not flowing. So how does BackboneFast improve on this? For that, we are going to go back to the whiteboard. Let's redraw our topology. So here I have Cat1, I have Cat2, and Cat3. I have the links between them. This one here is the root. This is FastNet 24, FastNet 24, FastNet 20, same here, and FastNet 22 on this side here. Now, we know that this here is the blocking link, that this one here is the designated port, this one is the root port, designated, designated, and the root port. Let's again examine what happens when this link here fails. Cat2 is going to declare itself as the root. It is going to start sending the inferior BPDU frames. But now, because we have enabled BackboneFast on Cat2, on Cat1, and Cat3, when this frame arrives on this port here, what Cat3 can do is it can send out the root link query to Cat1 out of its root port asking Cat1, hey, are you the root? And if Cat1, or is this correct, is this the best path to reach the root? When Cat1 receives this frame, it's going to respond back saying, yes, this is correct. This is the best path to reach the root. When this happens, and this is going to happen very quickly, this port here is immediately going to transition into a listening phase, which means that we don't have to wait for max age to expire. In listening phase, we are going to spend 15 seconds, then we are going to go into the learning phase for 15 seconds, and finally, we are going to move into the forwarding state, which means that it is still going to take about 30 seconds for this convergence to happen, but we don't have to wait those additional 20 seconds. Let's see this in action. I'm going to go back to my terminal, where in the meantime I have undid all the changes that I have done before. So now all the links are back and operational, and if I do show spanning tree on Cat1, I'm going to see the two interfaces. On Cat2, I'm going to see the two interfaces, and on Cat3, I'm going to see the two interfaces. And as expected, FastNet 20, the one facing Cat2, is in a blocking state. I'm now going to go and enable spanning tree BackboneFast on Cat3. I'm going to do the same thing on Cat2, and I'm going to do the same thing on Cat1. Before I proceed to shut down the link between Cat1 and Cat2, which I'm preparing right here, I'm going to go to Cat3 and I'm going to enable the debug of spanning tree events, and I'm also going to enable the debug of the BackboneFast. The command for that is debug spanning tree BackboneFast. So I'm going to go to Cat1 and I'm going to shut the link down and then immediately go to Cat3, and let's observe what happened there. The first thing that I see here is that I'm hearing from the new root. This is because Cat2 now thinks it's the root. The next thing here that I see is that I have received an inferior BPDU on FastNet 20. That's the one facing Cat2. I'm sending the RLQ request PDU towards Cat1 on FastNet 22, and I have received a response on FastNet 22. Cat1 confirmed that that indeed is the best path to reach the root, and I can see here that immediately FastEthernet 20 moved into the listening phase. I didn't have to wait for 20 seconds to expire before I moved into this phase of operation. Now, when this happened, my port facing Cat2 started sending BPDU frames. Now, the forwarding of the production traffic, of the data traffic from the stations that may have been connected behind Cat2 and Cat3 is still not flowing through this interface, but Cat2 is now forwarding the BPDUs received from Cat1, which had the result that Cat2 now received a superior BPDU frame and is generating the topology change here on Fast Ethernet 20. So I'm receiving the topology change notification generated by Cat2 as the result of receiving a superior BPDU. And then finally, we are going to move into the learning phase. We are going to change, we are going to generate our own topology change notification because now we are transitioning into the forwarding state. So we can see here that we have bypassed the 20 seconds of waiting time before, that we have bypassed the 20 seconds of waiting time that was originally there as the result of the max age. So this is what BackboneFast does. But before I proceed and just end here, because this is what the BackboneFast is, let me just show you this bit here in Wireshark. I want to show you these root link queries flowing through. So I'm going to go ahead and I'm going to do no shutdown on the link between Cat1 and Cat2. And I'm going to prepare my monitoring on Cat3. I'm going to say monitoring session 1, source interface, Fast Ethernet 22. I want to monitor traffic going in and out, and I'm going to send a copy of this traffic to Fast Ethernet 03, and I'm going to preserve any markings that I may have on these frames. And here, what I'm going to do is I'm quickly going to enable the filter that I don't want to see any loopback frames, I don't want to see CDP, and I don't want to see DTP. The only thing that I want to see here are really other frames. Because I don't have any other traffic, this will be the spanning tree frames, and these would be the frames that may be something other than the protocols that I'm filtering out here. So now I'm going to go back to Cat1 and just make sure that my spanning tree is now in a pristine state. That means that all the links are operational. So here on Cat2, I see the same thing, and on Cat3, if I do show spanning tree, I should be seeing the familiar situation that Fast Ethernet 20 is blocking. So now I'm going to go to Cat1 and I'm going to say shutdown. Before I do that, I'm going to restart my capture here, and I want to observe what is happening. And I was actually very lucky because the very first two frames that I'm seeing here are the root link queries. So I can see here, this is the actual query being sent out, but because this is a very, very proprietary protocol from Cisco, Wireshark cannot really decode it. All I'm getting here is just data. It doesn't understand this protocol, but we know what it does, so we can kind of look backwards and understand what is going on. So this was the query, this here was the response to the query. And as the result, we can see that the topology change has actually happened in our network. We have seen now how BackboneFast works when it's configured properly. In other words, when it's configured in our entire network, which is one of the prerequisites for the operation of the BackboneFast. But what would be the result? What would be the behavior in our network should we turn off BackboneFast on one of our switches, like for example on Cat1? Let's try that out. So I'm going to go to Cat1 and I'm going to say no spanning tree BackboneFast. It is now turned off on Cat1. I can confirm that if I do show spanning tree BackboneFast, and I get the result that the BackboneFast is turned off. It is still on Cat2 and on Cat3. So show spanning tree BackboneFast here on Cat3 shows me that the BackboneFast is turned on. Let's now try to turn off the link between Cat1 and Cat2 and observe the result on Cat3. So here I am going to Cat1, interface fastnet 24. I'm going to prepare this link for shutdown, but before I do that, I want to confirm that my debugs on Cat3 are still running. I'm running the debugs for the spanning tree events and for the BackboneFast. So now I'm going to go to Cat1 and I'm going to say shutdown on our link. Let's see the result. What I'm seeing here now are the hellos, the BPDUs coming from Cat2. And I can also see that Cat3 is sending the root link query requests on VLAN 1 on fastnet 22. It is sending the RLQs to Cat1, but Cat1 now cannot respond, which means that we are going to be receiving these BPDUs from Cat2 until the max age expires. In other words, configuring BackboneFast on Cat3 and Cat2 did absolutely nothing in our network to improve the convergence time because we didn't turn it on Cat1. And this is the reason why the BackboneFast needs to be enabled in the entire network in order to be fully operational.